Have you ever stopped to wonder why time only moves in one direction? It seems like such a simple, obvious fact of our existence. We are born, we grow older, and we remember the past, not the future. The coffee in your mug cools down. It never spontaneously heats up. An egg, once scrambled, can never be unscrambled. These are the fundamental rules of our daily lives, so ingrained in our experience that we rarely question them. But in the grand tapestry of the cosmos, this one-way journey of time is one of the most profound and persistent mysteries that physics has ever encountered. It's a riddle that has perplexed the greatest minds for centuries. The laws of physics, from Newton's mechanics to Einstein's relativity, are surprisingly ambivalent about the direction of time. This undeniable forward-marching property of time is what physicists call time's arrow. So, where does this arrow come from? If the fundamental laws of nature don't seem to care about past or future, why does the universe at large care so deeply? The search for an answer takes us away from the familiar world of clocks and calendars and into the very heart of thermodynamics, the science of heat and energy. It leads us to a strange and powerful concept, a measure of disorder and randomness that seems to be woven into the fabric of reality itself. This concept is called entropy, and it might just hold the key to understanding why yesterday is always behind us. To begin our journey, we must first get to grips with this idea of entropy. In essence, entropy is a measure of disorder, randomness, or chaos within a system. Imagine your bedroom. It's much easier for it to become messy than it is for it to become tidy. Imagine you have a box containing 4 coins. If you want them all to be heads up, there's only one specific arrangement that achieves this. This is a state of very low entropy. Now, what if we wanted a state with 2 heads and 2 tails? Suddenly, there are many more possibilities. In fact, a quick calculation shows there are 6 different microscopic arrangements that result in the same macroscopic state. The universe, with its trillions upon trillions of particles, operates on this very same principle, but on an unimaginably vast scale. If you take a brand new, perfectly ordered deck of cards and throw it into the air, the chances of it landing back in its original perfect sequence are astronomically small. This is not because of some mysterious force of chaos, but pure, simple statistics. The universe is constantly shuffling its components, and just like shuffling a deck of cards, it almost always lands on a configuration that looks random and mixed up. Another powerful way to understand entropy is to think about it in terms of energy, specifically heat. A hot cup of coffee doesn't stay hot forever. Its heat energy naturally flows outwards into the cooler air of the surrounding room. This flow of energy is always a one-way street. A state where heat is concentrated in one small place is a very ordered, low-entropy state. It's why a star shines. The incredibly concentrated energy in its core radiates outwards into the vast, cold emptiness of space, increasing the entropy of the universe with every photon it releases. This statistical foundation was the brilliant insight of the Austrian physicist Ludwig Boltzmann. He was the one who redefined entropy in terms of the number of possible microscopic arrangements, linking the macroscopic world of heat and engines to the microscopic world of atoms and probability. This formula, now carved on his tombstone, links entropy to the number of possible microscopic arrangements, a direct bridge between the world we see and the frantic, unseen world of atoms. Sadly, Boltzmann's ideas were so far ahead of their time that he faced relentless opposition. He tragically took his own life in 1906, just a few years before experiments would provide definitive proof of the existence of atoms, vindicating his atomic view of the world. Think about any event you can remember. You can always tell which came first. The intact glass is the past. The shattered pieces are the future. In every single case, the past is the state with lower entropy, and the future is the state with higher entropy. This thermodynamic arrow of time is the reason our memories are of the past and not the future. To form a memory, our brain must create new connections, a process that requires energy and increases the overall entropy of the universe. It is the unstoppable increase of entropy that provides the script for the unfolding cosmos, ensuring that events proceed in a logical, ordered sequence. Scientists believe this incredibly ordered state was the Big Bang. Around 13.8 billion years ago, all the energy and matter in the observable universe were compressed into an unimaginably hot and dense point. This was remarkably ordered in thermodynamic terms. Think of it like a perfectly wound-up clock. The Big Bang wound up the cosmic clockwork, creating a state of immense potential and low entropy. Ever since, the clock has been unwinding. Every star that shines, every planet that forms, every chemical reaction that occurs is a part of this unwinding process. Our very existence as complex, ordered beings seems, at first glance, to defy the second law of thermodynamics. Life does not exist in a closed box. We are open systems, constantly exchanging energy and matter with our environment. The order we create within ourselves is paid for by creating an even greater amount of disorder in the world around us. Life is a beautiful, complex eddy in the great river of entropy, a temporary pattern that exists only because the river is flowing downhill from the Big Bang's low entropy towards a future of high entropy. For a long time, black holes seemed to pose a serious threat to the second law of thermodynamics. It seemed as though you could make entropy disappear from the universe. The breakthrough came from the brilliant work of Jacob Bekenstein and Stephen Hawking in the 1970s. Hawking showed that black holes are not completely black. They should radiate a faint glow of particles, now known as Hawking radiation, proving that black holes perfectly obey the second law. This stunning discovery linked the three great pillars of modern physics and proved that entropy is a fundamental property of the universe, woven into the fabric of spacetime itself. However, some physicists and philosophers argue that this might be putting the cart before the horse. The crucial question is, does entropy's increase cause time to move forward? Or does the forward movement of time cause entropy to increase? It's a subtle but profound distinction, a classic chicken or the egg problem at the heart of modern physics. The arrow of time is not a single, simple concept, but a collection of different arrows that all point in the same direction in our current universe. The great puzzle is why they are all so perfectly aligned. And so we are left gazing at the heavens, armed with a beautiful idea but still facing a deep puzzle. The link between entropy and time has revolutionized our understanding of our place in the cosmos. It tells us that our complex existence is not a defiance of nature's laws, but a temporary and beautiful consequence of them, a fleeting pattern of order riding the great cosmic current towards disorder. The simple, intuitive feeling of one moment passing to the next is tied to the grandest story of all, the story of the universe itself, from its special beginning to its ultimate, uncertain end. The question continues to fascinate because it is not just about physics, it is about us.